This video is a continuation of the last one. In the last video, we went ahead and performed what's called an unconstrained optimization. It's unconstrained because there is no constraint imposed on the optimizer. It's allowed to find the minimum without any constraints. Now let's focus on an example that does have a constraint. Here, our new constraint function is defined as g1 is equal to x1 squared plus x2 divided by 2 squared. We're going to say that the solution should always be greater than a value of 1 for g1. So you can imagine this is our graph, and the constraint is saying that anything outside of the ellipsoid is a satisfied constraint. So now let's go over how to define this in the Nastran Solution 200 web app. Most of this example has already been constructed from our previous video, so we can continue from where we left off. So here, let me go ahead and maximize the screen. I think we don't have to worry about the variables or the objective. It would actually be a good idea to recap what the optimization problem statement is. The optimization problem statement is basically an explicit definition of what you want to optimize. What's your objective? What are you going to vary in your finite element model? What are your constraints? This is very similar to the previous optimization problem statement where we defined our objective function and design variables. Here again, the new thing is a design constraint. So now let's go ahead and define that here in the web app. Again, I've already defined variables, the objective, and now it's time to define our constraints. So here, there's a section called Add Equation Constraint. This is where you can explicitly define your equation constraints. So I'll go ahead and take a few moments to do that for us. And again, the lower limit is 1. So we are saying that as long as the solution is greater than 1 for G1, that's a satisfied constraint, if you will. So now let me take a quick look at my notes just to make sure I typed this in correctly. And now we can go to the exporter once we created our constraints. We'll go ahead and download this new package. And like before, we'll go ahead and perform the operation to start Nastran for us. And while this is happening, let's go ahead and take a look at what we expect to happen. So like before, the optimizer will go down the steepest path to the global minimum, if you will. But then it encounters this scenario. Again, anything outside of the ellipsoid is a feasible design. Feasible means that your constraints are satisfied. You can see that at the initial analysis, the constraint is satisfied. You're outside of the ellipsoid. By the first design cycle, you're still within the feasible region. But notice what happens around the second design cycle. You can see it actually went into the ellipsoid. The interior of the ellipsoid will create a violated constraint. So this constraint would not be true if you're inside of the ellipsoid. This region inside is known as the infeasible region, or the region that has constraints that are not satisfied. The optimizer then corrects this by going to the boundary of the ellipsoid. Again, anything on the outside or on the boundary is still satisfying the constraint, and then moves along the constraint until it finds the very minimum here. Let's see if I can zoom in and rotate the model so I can see what the minimum is. Let me rotate this up. Maybe this will help. And here, if I recall, the minimum was at 1, 0. You have to be very careful with this. So the minimum is at x1 equal 1, x2 equal 0.05, and a vertical value of 1. So let's go ahead and view the results. And let's see what we got. So here we have the value of 25, and we went all the way down to 1. So this does match the solution we have here in our plot. let's go ahead and look at the design variables. So the first design variable here in blue started at a value of 3 and it went all the way down to a value of 1. The second design variable went down to a value of 0.05. And here if we look back, that's exactly what we have here on the graph. So this is a constraint optimization example. There's also another thing I would like to cover. That is the normalized constraint. I know when I first started using Nastran Solution 200, this specific table or this information really confused me. I thought this was actually the value of the constraint equation, but this is actually the normalized constraint. So here, let's just go ahead and look at a separate tool. If you go to the results section and open up your responses F06, this is a tool that can let you inspect the F06 file. Here are all the quantities for the equations I defined, the objective and the constraints. Here, for example, this row R0 is my objective function. You can see the value at the very beginning is 25. So this corresponds to the value that you see here in red. So here in red is the initial design. So this is 25. Now, let's look at what's called active constraints, or rather, let's look at maximum constraint for each design cycle. So here in this column value, this is the actual value of the constraint function we defined. So that would be g1 is equal to x1 squared plus x2 divided by 2 squared. So the value, that is the value of the constraint equation. What's being reported in this normalized constraint section is what's called a normalized constraint. So this is a combination of the lower bound and the actual value of the function. If you refer to the Nastran Design Sensitivity and Optimization Users Guide, there's a big section on what the normalized constraint equation is. But I just wanted to let you know that this plot is not the actual value of the constraint. It's a normalized value. So here, if you look at this table, the first normalized constraint value is about 0.187. And then if you look here, the first normalized constraint value is 0.187. Here it's very small, almost to 0, and so on and so on. So here, if I look at the fourth design cycle, and if I look at my responses here I get negative 5.68 to negative 3. And this matches what I had here on this normalized constraints section. So now that you know that this is actually normalized constraint plots, these are what are governing the optimization. Here we see that for each design cycle, the only constraint that's essentially influencing the optimization is the function g1, or in this case r1 that we define. This r1 is actually the label that corresponds to the constraint. So here you can see we've defined this equation. R1 is equal to this expression. Also, if we look at R0, this is our objective equation. So again, the values are reported here on the right. Now, in the next video, we are going to cover what are called side constraints.